Let's take a look at this first section in our new unit. Our new unit's Unit 2, and we're going to be focusing on Chapter 7, where we're going to be studying the quadratic functions. We're going to start by taking a look at the quadratic function in the vertex form, which is actually section 7.6. Now, the goal of what I'm trying to achieve here is to help you identify and be able to graph quadratic functions when they're in the vertex form. There will be some vocabulary that we'll need to start to include in our conversations together. So make sure you watch for these in the video and record them. Vertex, axis of symmetry, maximum, minimum, domain, and range. Make sure you copy those down and remember that these are things that we're going to be talking about in the next weeks, actually, as we discuss quadratic functions. Now, we started by looking at the following picture, which is a beautiful picture of a dolphin which is jumping. It's left the water, as you can see down here, and it's jumping in this beautiful arch. And if the dolphin were to continue this pattern, we would get what is known as the parabolic shape. And the beauty of this is that this parabolic shape can actually be described using this function that we're going to learn about, the quadratic function. As we discussed in class, this is not the only thing that creates this shape. In fact, anything that is thrown, and once it leaves your hand, so once it's a projectile in motion, it will follow this pattern, whether it's a softball being thrown or a football, whether it's a soccer ball that's being kicked, whether it's someone that's driven up on a bicycle on a ramp and just in a free fall, you create this beautiful parabolic shape. So if we were going to ask to find the actual quadratic function for this dolphin that's jumping in the air, what might we want to know? Well, we might want to know how high he jumps. How high is he actually jumping as he goes here? If we pretend on our graph that this is 0, 0, where he left the water, how far does he go before he gets back in the water? You might ask, how fast is he going and what angle did he come out of the water? There are a number of different pieces to this, but we will be looking at this later and trying to decide, if I give you some information, can you create a quadratic function for me? So first, let's remind ourselves of some of the mathematical functions you already know. Keep in mind that a function mathematically is an equation which creates a graph for us. It's an equation that does something. It creates a graph. So looking at this one, we see that we have a graph. This graph is y is equal to 3. We sometimes call this a constant function because it is flat and doesn't change. You could also say it's linear, but its equation is y equals 3. When I look at the following equation, or a function, I see a linear function, a line. And if I were to ask you what is the equation of this function, well, you'd have to know, well, let's say that this crossed at -1 and crosses 1. Then we could take a few minutes and we would come up with an equation something like y is equal to x plus 1. And that equation is a function which describes this line that we have in front of us. So now the new one, and most of you recognize this. This is a parabola, and a parabola, that's the shape that we're talking about, this lovely little curve that we have. And this parabola can be described as a quadratic function. So the name of the shape is parabola, the name of the function is quadratic function. And just so that you recognize what's happening here, if you were to describe this quadratic function as if you were a little insect crawling along this line, as you're coming along this way and you're watching what the graph is doing up above you, you realize that the values are coming down and down and down. They're decreasing, we say, until they get to this spot right here at the bottom, and then they start to increase. So it decreases and increases. And one of the things about quadratic functions that makes them unique from the linear function is that they change directions like that. Whereas the linear function was always either rising or falling. It never changed directions. So there are a few vocabulary terms that we need to make sure you understand. First of all, the line that goes straight down through the center is what we call the axis of symmetry. And if you look at the parabola on both sides, it's a mirror image of itself. This little point that sits at the bottom of our graph is called its vertex. If it has a vertex down at the bottom like this, we say that it is a minimum value. If it has a vertex at the top, like this one, we say that it is reaching a maximum value. If I had gave you a graph like this and said, how would you describe the domain of this function? Well, if I'm thinking about this insect that's traveling along in this part, the graph is taking place up above and it's going everywhere. This continues infinitely. So we would say that x is an element of the real numbers. Whereas for the range, if we think about it from coming down from the bottom and up to the top, we realize that the graph doesn't begin until 0 and then it goes on forever. So we would write that y is an element of the real numbers such that y is greater than or equal to 0. So the real question that we're looking at is, what is the equation of this function? What makes him different algebraically from the linear function? Well, y is equal to x squared. That is what gives it its distinction. If you remember, for linear functions, the x is only to the power of 1. So in class, we took some time and started to play around with this to see if we could see what happens to the equation as we start to change it. So we did this first exercise with our graphing calculators, and we graphed y is equal to x squared, and then x squared plus 3, and x squared minus 5. Now, for those of you who don't have access to a graphing calculator, what I'd like to do is show you an online resource that you have. So let me just move things around a little bit. I'm going to escape here for a second, bring this up, and I need to go to my Desmos. Take a look at the address that you see up above. It's desmos.com/calculator. And this is what you will see. It's actually an online graphing calculator. To use it, you're going to go over to the side and you're going to type in y equals, and you're going to use x, and you can use the squared right here. And there you have it. It's your first one, y equals x squared. If, when you're using the Desmos, it isn't already up, then you can just press this little hidden keypad down at the bottom left, and it will come up for you. Let's take a look at the next one. So y equals x squared plus 3, I think it was. Now, if we watch what happened, we realize that, hey, the vertex moved up 3. And if we try the next one, y equals x squared minus 5. And with this one, I got to get out of here. So you realize that, hey, the vertex went down 5. So you can play around with this and use some of the exercises that you're going to see on the rest of this PowerPoint and do them yourself. I would pause my video and give it a try with Desmos if I were working on it with you, just so you can get used to it. But the first thing that we notice is that when we add numbers on the end like this, it moves the graph up and down. And this is a snapshot of what it looked like, which we did. So here's a general description of it. X squared plus q means that the graph of y equals x squared moves up and down by the value of q. If q is a 3, it moves up 3. If q is a negative 5, it moves down 5. All right, the next one we tried was this one, and you'll notice that now the numbers are inside with the x's. And so take a moment yourself and try to figure that out on a graphing calculator. Here's an example of what it actually turned out to be on Desmos. Here was the x squared. When I added 3, it went to the left 3. When I subtracted 5, it went to the right 5. That seems to tell me that my motion is moving left and right, and that it moves in the opposite direction that I would think it would. So going to the general example, if I have a number, and I'm going to call it negative p, and notice that this whole thing is still squared. That's how we know it's a parabola. Then the graph of y equals x squared moves left and right by the value of p, and notice that p changes its sign. So if it's negative p here, it's positive p that it's moving in its direction. This leads us to a really important conclusion. Here you have a quadratic equation in what is called the vertex form. And we say that because the vertex is very easy to see. We know that the numbers that the graph is going to move up and down are here with q, so that's the y value, and that the left and right motion is here with negative p, so that's the x value. So our vertex is simply p, q. And which I said before, but the quadratic function, when it is in this form, it is called the vertex form because we can pick out the vertex so easily. Okay, so some more motions that we wanted to do. So we did a couple of them. First of all, we put a negative in front, and then we put a 3, and then we put a 1/3. And let's see what happened. So your original, I put it over here so you could see the colors and keep them straight. The original one is red. And when you put a negative in front, it flips over the x-axis. We say it reflects in the x-axis. When you put a 3 in front, it got really skinny. It's the green one because the values, it's almost like the slope gets steeper, but we don't talk about it as slope because it's not constant, but it does, the sides get steeper. And then for the 1/3, it's the purple one. So it starts to get a little flatter. So we describe this in this way. If you put a number in front of the x squared, if that number is less than 0, the graph is reflected in the x-axis. If the number is greater than 1, like the 3 that we did, then the graph is expanded. It gets, I like to say it gets skinnier or steeper. And if I put a number in a fraction in here, something between 0 and 1, then it is compressed, or the graph gets flatter. Now this leads us to a very typical type of question where I give you equations and I ask you to find the vertex, the axis of symmetry, the maximum and minimum, the domain and the range. Now I'm going to go through these with my solutions and I'm going to start from the bottom one and work up. So I would suggest that you freeze now, try this one, stop it, and then go ahead and try the next one and so on, just to test yourself on what you're doing. So the first one, my vertex comes, here's this one, is +2, -3. My axis of symmetry would be x is equal to 2. Here's a quick sketch of it so I could see what it looks like. Here's 2, -3, and I know my graph is opening up because there's no negative out front. So it has a minimum value of y is equal to -3. Sorry, my vertex is a little bit off of my drawing. The domain is x is an element of all real numbers, and the range is y is an element of real numbers, but y is greater than or equal to -3. The next one. This one gives me a vertex when there's nothing here. The x is a 0. So it's a 0 and a 1. The axis of symmetry, x equal to 0. Now I'm going to draw it. Here's my 0 and 1, and I know it's opening down because I see a negative here. So I have a maximum this time of y is equal to 1. My domain is the same, and this time my range is y is less than or equal to 1. Another one. This time there's nothing at all, so my vertex is 0, 0, and my axis of symmetry goes straight through where x is a 0. I've drawn my graph, keeping in mind that this was a negative, and it's going down. So the domain is still x is an element of the real numbers, and the range is that y is less than or equal to 0. The last one. Once again, there's nothing there, so my vertex is 0, 0. Axis of symmetry then is still x equals 0. I drew my graph. It's opening up because this is a positive number. I can see it is now, oh, I've made a mistake. This should be a minimum of y equals 0. So make sure you take a correction to that. That should be minimum. And the domain is the same. And the range, ooh, I'm also making another mistake. You can tell I'm tired at the end of the day. Y is an element of the real numbers such that y is greater than or equal to 0. So make sure you correct that as well when you're looking at it. Okay, so sketching. Well, in terms of sketching, if I ask you, and literally I really should have put, in fact, let me go back and change that, because when I ask you to graph, I'm looking for more accuracy than an actual sketch. And so this one really should say graphing rather than sketching for it. So I'm going to change that so you know. I will expect you to find the vertex and put it in place, to draw the axis of symmetry, and to find the y-intercept and the point that's opposite to it. So let's take a look at what that looks like. So here's my function. My vertex would be -3, -5. So I put that in place. I have to draw the axis of symmetry. It goes straight through where x is equal to -3. To find the y-intercept, I know that x is a 0. So I plug in a 0 here, and I go ahead and carry on with my calculations. When I have this, this is 9/2 minus 5. So I get +1/2? It's -1/2. I was trying to make sure that I hadn't done the wrong answer there as well in my haste. So it is -1/2. So my y-intercept is here at 0, -1/2. Now, the point that's opposite to it on the other side of the axis of symmetry is directly across. This one was 3 units this way, so this is 3 more units. That's why it's -6, and it's down at -1/2. What that does is give you a good idea of how wide your parabola is when it opens. Okay, so example 3, where we can give you an equation and ask you, or give you a graph, sorry, and ask you to draw the equation. So I'm going to start with the one on the left to start with. What I'm going to pull out is the fact that the vertex here, now the vertex is -3 and 4. And I also want to take note that the graph goes through this point right here, which is -1 and 2. So let's see what we do with that. Vertex -3 and 4 and through -1 and 2. So what I start out doing is putting in the vertex in my formula. Y is equal to, I put an A there because I don't know what it is. I don't know what the number is in front, but I know that the -3 becomes +3 and that the 4 goes here. Now this graph is going to pass through this point. So I'm going to use these points, plug them in, -1 there and 2 there, to figure out what A is. So you can follow through the math and check to see what it is. It looks like it's -1/2. A is -1/2, so I put it all together. Here's my equation, y equals -1/2 onto x plus 3 squared plus 4. This is the equation of that graph in vertex form. Now I'm going to do the middle one. What I notice is that the vertex is 0, -3, and then it passes through 1, -1. So you can stop and take a look at what I've done and just follow through. It looks like the A turns out to be a 2 this time, so I plug it in and I'm off and running. The one on the far right, I can see that my vertex is 3, -2, and that it passes through 4, -3. And so following the same process I've used before, first I put my 3 in and then my -2. Notice the sign changed, and -2. And then it's going through this point. So I plug those into the X and the Y position and find out that A is -2. And then I'm good to go by putting it all together. So there are a couple of remaining questions that I asked just to make your brain hurt a little bit. If you think about it, will all parabolas have x-intercepts? People stopped and thought about that and realized, you know what, if the vertex is up above the x-axis and the graph opens up, then it'll never cross the x-axis. And similarly, if the vertex is down below the x-axis and it opens down, it's never going to touch it. So no, it's not always going to have x-intercepts. Will all parabolas have a y-intercept? Well, because parabolas are infinite, they will keep on going. So no matter where they're located, they will eventually cross the y-intercept, the y-axis. Let's go back to our question then about the dolphin, and let me give you some more information. So let's say that this was, I put the values for where the dolphin was on a graph, and I want you to give me the equation. We can see the vertex is 3 and 7. It passes through this point, which is 9 and 4. So we use our same method that we did in those earlier questions. We put in the 3 as -3 plus 7. Goes through 9 and 4, so we plug it in. And when we do our math carefully, we realize that A is equal to -1/12. So just stop and take a look at that math. I'm hurrying because I don't want the video to be too desperately long. And so then I know what A is, so I plug it in and use it in my equation. So there you go, everybody. You have now learned how to identify and graph quadratic functions in the vertex form. Your homework was located here, and I'm pretty sure that's the correct, it looks like the correct version, so good luck with your homework.